Okay. So today we're going to talk about the differences between integer solutions and real value solutions. And so I'm going to start with one of my favorite calculus problems. Although at first it is not going to seem like a calculus problem. So consider the following absurd situation. You have the number n is 100. And for some reason, you are obsessed with the following. You want to write n as a sum a1 through ak. Each ak is at least 2 and is integer. Well, we'll make it at least 1 integer. And your goal is you want to maximize a1 times a2 times ak. So there are two things here that make this different from a standard problem I would give you in calculus. What are the two differences?
AK is an integer.
So the first thing good is that things have to be integer valued. And whenever we use the techniques from calculus, we're always looking for, what's the best real solution. What's the second complication?
It's not continuous.
What do you mean by it's not continuous?
Integers are not.
Okay, so that's the problem with the integer part. But there's another problem here. It's more than just the integer. There's another complication here.
AK greater than equal to 1.
We don't know how many k.
We don't know how many k's. These constraints aren't that bad. We've had constraints like this in calculus before. It's that we don't know how many k's there are. Now, of course, one way to do this is to find what is the best when k equals 1, k equals 2, k equals 3, k equals 4, and solve it for each choice of k, and then look and see which value is the best. So that's one good attack. So attack, fix k, let f of k be best, and then optimize. So that's one way to attack the problem. Okay, any thoughts or any conditions or constraints that we might want to put on this problem? How would we try to go about this? Can you tell me any things about the AKs? What would be a poor choice of an AK?
Or to be 1.
1, right? If I take any of the AKs to be 1, that doesn't help the product. Right? We could always just combine it to something better. So, never take an AK equals 1. Okay. What about the opposite extreme? Can you tell me a number that's so large, I would clearly not want to take that as an AK, as one of my values of my A's?
100.
100. Why wouldn't I take 100?
K equals 1, and then the goal, like the maximum is just 100.
Okay, maybe that's the best I can do.
But if it's 50 and 50, and then what you get is 2,500.
Okay, good. So we know that we don't want to take any of the values to be 100, because we could split up into 50 and 50 and we would do better. What about 99? Could we ever take any of the ones to be a 99? What could we split 99 into?
1 and 99.
Not 1 and 99.
So you let n equal 99?
No, I'm saying n is 100. And I want to choose the values of my A's. So you just told me that, the best is not to just take one of the A's to be 100. Because if I replaced that 100 with a 50 plus 50, I could do better. What if one of my numbers was a 99?
It's even worse.
What could I replace 99 with?
49, 50.
49 and 50. Okay, what about 98? What could I replace 98 with?
249.
249 is okay. Dot, 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 dot. All right, let's go all the way down to 10. What could I replace 10 with?
2 5.
2 5s. How about 9? 5, okay. 8. Come on, let's do this fast. Okay, 8, 4 and 4, 7.
3 and 4.
Right, because 3 times 4 is 12, right?
2, 4.
So 7 versus 3 plus 4, 3 plus 4 wins. Okay, what about 6?
3.
Okay, so 6 versus 3 plus 3, 3 plus 3 wins. What about 5?
2,
3.
Which ones?
2, 3.
So this wins. What about 4?
The same.
It's the same, it's a push. What about a 3?
3, 1.
3, 1.
Would I want 3 ones? Does that help the product?
No.
No. So if I have just 1 3, I don't want to break it down any further. So what we've just shown is there can't be any number larger than 5 or higher. Everything is at most 4. But if we wanted to, we can say there's no 4s, because I can always replace a 4 with 2 2s without any loss. So we know we only have 2s and 3s. Okay? So that's not bad. You know, in just a few lines of work, we now know we just have 2s and 3s. Okay. So which do you think is better? Lots of 2s or lots of 3s? So we're going to have some number of 2s and some number of 3s. Which would you rather have, lots of 2s or lots of 3s?
3.
Why?
3 squared bigger than 2.
Yes! 3 plus 3 versus 2 plus 2 plus 2. This has a product of 8. This has a product of 9. Every time we see 3 2s, we would want to replace it with 2 3s. And so our answer is going to be almost all 3s with either 0, 1, or 2 2s. So, you know, I don't know what the actual answer is. I always forget. See, 32 times 3 is 96. And maybe we have 2 twice as 4. That might be the best we can do. I'll leave it to you to figure out exactly what the best is, but it's pretty clear what it is now. You know, we're going to have either 0, 1, or 2 2s. We won't have 3 2s. And if we only have 1 2, we're going to have a problem because it's not going to be a perfect multiple of 3, so we'll have an extra 1 floating, and that 1 could combine with either the 3 or the 2. So we're not going to have 1 2. So we'll have 2 2s. So I think it's 32 3s and 2 2s. There's a deep reason why we have more 3s than 2s. What are the greatest constants in all of mathematics? Think of big constants in math. What are the first constants that come to mind? Pi. What else? Try again. No other constants come to your mind in math?
Natural number E.
Ah, the natural number E.
Yeah.
What can you tell me about E? Approximately.
2.6.
2.6? No. 2.7182818.
It's not that bad.
It's a fundamental constant. Fundamental constants should be known to at least 6 decimal places. Of course, you can choose which base it is, and then 6 decimal places isn't as bad. Okay, there is E at 2.7. Here's 2. Here's 3. Which numbers are you closer to? So your 2.6 would actually be sufficient for what I need. I just need that it's past 2.5. E is closer to 3 than 2. And that's what's going on here. So what I wonder is, I want to now analyze an analog of this problem. And this is going to talk about the difference between integer solutions and real solutions, and then use this as a springboard to talk about linear programming. So again, when you have an integer solution, the optimal integer solution does not have to be near the optimal real solution. That's one of the big problems. In a lot of linear programming, we are forced to have integer constraints. You know, the plane takes off or it doesn't. We are not flying Schrodinger's airline, where the plane is in a superposition of flying and grounded, right? You know, the plane is either flying or it is not. So, if I want to generalize this problem, all I have to do is kill basically 1 or 2 words. What words do I have to kill?
And integer.
An integer. And now the problem's more interesting. I'll clearly keep each of the a's to be greater than or equal to 1. And so now the question is, what is the best way to write n as a sum of non-negative real numbers? Each is at least 1, such that I can maximize the product. Because again, if one of the numbers was less than 1, I could just add it to something else. Okay. Now, a lot of our arguments from before still apply. We're not going to have any numbers larger than 5. Right? Now we have to be a little bit more careful. We would still, a number like 4, we could still break up 4. That's basically like a pivotal point. How far down could we go? Would we want a number like 1.1? So sometimes you have to figure out how far do you want to analyze the problem for your work. So what we're going to do is before is we're going to let fk equal the best with k summons. And so what we're going to do is we're going to evaluate this for each k, and then we're going to optimize on k. So we're basically doing 2 optimization problems. We first fix k and find what is the best way to fragment 100. And then, once we do that, then we're going to see of all these which k is best. So just to recap, we just did the integer case. Now what we're trying to do is we're taking a number like 100, and we're going to split it into k sums and see what's the best way to do this. So what's your intuition? What do you think will be true at the optimal splitting?
As close as possible.
I'm sorry?
Each AK is as close
As possible to what?
to
To e, right? You're going to see that the optimal splitting is you want each of these summons to be approximately e. Now, if I give you an integer like 100, you're not going to be able to do that. But, okay. Let's say now that we've decided we want to have exactly k summons. Do you think all the summons are the same or different? Same. And so this goes back to the classic Farmer-Brown problem. So the Farmer-Brown problem is, Farmer-Brown is obsessed with rectangles and poorly drawn cows. Okay? And he wants to know if he has a certain amount of fence, what's the maximum area he can have. So if this is x and this is y, 2x plus 2y equals the amount of fence. Well, this is the same as x plus y is just the amount of fence over 2. And Farmer-Brown wants to maximize x times y. Well, we could solve this using multivariable calculus. Or we could solve this by saying, well, let's reduce this to one variable. This is maximizing x times f halves minus x. If we multiply this out, we get f halves x minus x squared. We take the derivative, and we get f halves minus 2x equals 0. So the critical point is going to be, yes. And in fact, that means the critical point for x is the same as that for y. So if we have 2 numbers, and they have a given sum, the largest the product can be is when the 2 numbers are the same. So I basically want to say that this implies if I have exactly k terms, the best I can do is when they're all the same. If 2 ones weren't the same, I could get a larger product by replacing those 2 values with their average. So briefly, when you have to decide, is this rigorous enough for you? Let's say we have a 1, a 2, a k, and A1 does not equal A2. Then we send this to A1 plus A2 over 2, A1 plus A2 over 2, A3, AK. And we've only increased the product. And so we keep playing this game. Now the problem is, does this converge? Does this converge to all the values being equal? Is that going to be the global maximum? You know, is it possible we could maybe somehow cycle among various points? Where maybe the first two become equal, then the second and the third become equal, but now that's different than the first, and now the first and the third become equal. So what you would have to do is you would have to play games such as look at the smallest value and look at the largest value. And every time you do this, the smallest value always goes up. And the largest value always goes down. And so it's becoming, you know, tighter and tighter and tighter. Well, maybe you can't quite say they always go down because maybe you had multiple things that were the smallest, multiple things that were the largest. So, you know, this is where you get all these different technicalities, but it should eventually iterate down to all of them being the same. Okay, so that's one way to see it. Another way to see it is the more standard multivariable calculus approach. But of course, if you're trying to do this in Calc 1, you can't use multivariable calculus, right? You could use Lagrange multipliers and say, you know, I have this constraint and I want to maximize this function. So my function is maybe a of x is a1, a2 of ak, and my constraint, my g of x, is a1 plus ak equals n. So the gradient of g, that's easy. It's all ones. What's the gradient of a? So I take the derivative first with respect to a1 and I get a2 through ak. Then I take the derivative with respect to a2 and I get everything but a2. So a nice way of writing the gradient of a is it's just a of x over a1, a of x over a2, such about a of x over ak. Right? This pulls out the factor of a1, this pulls out the factor of a2. So if I want these two vectors to be parallel, you know, Lagrange tells us that, you know, the gradient of a is lambda gradient of g. And I think we talked about Lagrange earlier in the semester. Do we care about lambda? No. You know, if we get lambda, that's nice, but our goal is to find the optimal solution. Lambda is a helping parameter. Well, this is easy. All of these components are the same. So all of these components have to be the same. Well, good. They both have the same numerator, so the denominators must be the same, so everything is the same. So if you want to do this entirely without multivariable calculus, you can. You have to do some kind of a little bit of an analysis trick to show that it converges to everything being the same. But we now get that the optimal value is when they're all the same. Okay. So we can now evaluate f of k. So remember, we said f of k is the best we can do with exactly k sums. So f of k is equal to, what's the common value?
What do you mean by
So we said that the best we can do for a given number of sums, we have k sums, is when everything is the same. So what would be the value? A1 equals A2 equals
100 over k.
100 over k,
times.
or more generally, over k. You know, if we want to do the 100, it would be 100 over k. The more general case is n over k. And then we just raise it to the k power. So this gives us our optimal function. And now we have to optimize the optimal function. Now, what can you tell me about k? positive integer. Let's forget about the integer part, shall we? Let's consider f of x is n divided by x dx, which is e to the x log n of x, where of course log is base e. All I'm doing is I'm taking this function and I'm evaluating it at all real values rather than just integer values. And what I want to do is I want to figure out where is this function largest. What I like about this problem is this figures almost all of Calc 1 in one problem. So now we need to plot this function. Okay, so what I'm going to do is just in the interest of space, I'm going to kill a bunch of this. And I'll write up here that we have f of x is e to the x log n of x. Alright, so this is a bit of a non-standard function. I don't think you've really seen this function before. But it's actually coming up naturally. And when we're done, I will even mention why this problem is important. This is not just a make-work problem. Alright, let's figure out how to graph it. If you want to get information about a function, what's another function that can help? The derivative. So let's calculate f prime of x. Well, we have f of x is an exponential, so the derivative is just the exponential again. And now we take the derivative of the exponent. So we have to use the product of the derivative of x is 1 times log of n over x plus x. Now we have to take the derivative of the log of nx. The derivative of the log is 1 over, so you get 1 over n over x. And now we have to take the derivative of n over x, so that should be negative n over x squared. So please watch the calculus. It's been a while since I've differentiated. Okay, I think that's right. Should move on. And of course, the other thing you could have written this as the log of n minus the log of x. And I might have cleaned up some of the algebra a little bit. Alright, so the derivative of log is 1 over 10 over x. Okay, good. So now, f prime of x is just f of x times the log of n over x minus, okay, the n's cancel, the x squareds come up, minus 1. Come on, isn't life good right now? Right? I mean, look at how beautifully everything simplifies. And what is really negative 1? Or 1? The log of e, right? But the log of e equals 1. So f prime of x is f of x times the log of n over x minus the log of e. Oh, but we like log laws, so that's just f of x times the log of n over xe. Right? So what I'm going to do is I'm going to erase the algebra, and I'm going to just rewrite over here what f prime is. So f prime is f of x times the log of n divided by x over e. Okay, because when we're trying to plot this, we don't have to be that good. We don't need great language. We don't need to do a phenomenal job of plotting this. We just need to do a good enough job to sniff out where's its maximum. So if the first derivative is positive, the function is increasing. If the first derivative is negative, the function is decreasing. So here's the x-axis. And here's f prime of x. Here's x equals 1. And let's see what happens. Well, if x is small, I'm going to be taking the log of a number that's close to n over e. That's going to be log of a positive number. The first derivative is positive. So my first derivative is positive for quite a while. And then my first derivative becomes 0. At what point do I get 0? N over e. And now, once x exceeds n over e, I'm taking the log of a number less than 1, so it's negative. So what I know is my function has to look like this. Something like that. It goes up monotonically, goes down monotonically. The best value is to take x to be n over e. And remember, we started off with f of k was n over k and k, and then we went to f of x is n over x to the x. So really, we want k to be about n over e. So this is the number of summons. Right? And each summoned, each AI is then approximately n divided by n over e, which is about e. So in the continuous case, we want each of our summons to be e. And then we have to tweak things a little bit about that. Now what I particularly like about this is we want to find not the best real value, but the best integer value. Right? If n is 100, I cannot take 100 divided by e. Where is the best integer value?
Need to check.
I'm sorry?
Need to check.
What do I need to check?
Like the biggest integer that's smaller than n over e, and the smallest integer that is bigger than
Good.
n over e.
All we have to do is check these. These are the only candidates. None of the integer values less than this can matter, because I'm increasing. None of the integer values past here can matter, because I'm decreasing. This is really nice. The optimal integer answer is near the optimal real answer. So, optimal integer answer is near optimal real answer. This is not always the case. And we're very fortunate to have this. And we were able to prove this without using too much in the ways of machinery. And basically, this is just Calc 1. You know, all that curve sketching that they make you do, all those log laws, you know, here's the reason why we want to know these. We just need a good enough sense of the graph to see what's going on. And so, without having to try all the different integer values, I know I just have to try these two and know which one is best. Okay. So there's a great deal of stability here. If I move a little bit away from the optimal real value, I'm still going to be close in value. I'm not going to have a massive change in the value. All right. Now let's go to linear programming, where the situation is sometimes violently different. Okay. So the standard version is called, this problem is called the knapsack problem. Okay. So we have a knapsack that can hold, I'll use kilograms, but almost surely the book uses pounds. So you can hold 100 kilograms. I'm sorry?
What is that?
Backpack. But you're required by mathematical convention to say knapsack. It's known as the knapsack problem. So you have a bag that can hold 100 kilograms. And you have three weights. A 51 kilogram weight, which is worth $150. You have a 50 kilogram one, which is worth $100. And just so I'm using the same notation that we have in the book. Let's see, what was that? And, okay. And the other one is 50 kilograms and is worth $99 per minute. Okay. So what do you think you're trying to optimize?
That is in each pack.
Yeah, the values in the knapsack. So you can hold 100 kilograms. So, if you can hold 100 kilograms, what's the first thing you can tell me?
I'm not gonna choose the 51.
Which 51?
The first
The
50.
50. We have only 151, right?
No, 51, 50, 50. We have two 50 weights.
Yeah, I'm
And for
not
each
choosing the
one.
51.
Oh, we're not going to choose the 51. Why?
Because I'm gonna have only 51.
Because then we can only put in 51, and that would only give us $150. If we choose two of these, we get 200. If we choose two of these, we get 198. So the solution is $2 of $100, and this yields $200 in our knapsack. Okay. Now let's tweak the problem a little bit. Rather than saying we have a 51 kilogram weight worth 150 pounds, let's imagine that now the first one is $100, I'm sorry, it's $150 for every 51 kilograms. The second was $100 for every 50 kilograms. And the third was $99 for every 50 kilograms. And we need to choose some number of each one. So we'll choose x1 units of the first, x2 units of the second, x3 units of the third. So clearly, x1, x2, x3 are greater than or equal to 0. x1 plus x2 plus x3, what can you tell me about that?
Less than or equal to 100.
Let's move to 100.
No, it's a number.
Now, is it less than or equal to 100 or is it equal to 100?
Equal.
Equal, right? Because if I had less than 100, I could just add more. And if you remember, in our canonical linear programming problems, we always have equalities, we never have inequalities. And now what do we want to maximize?
That thing times.
The dot product, basically, right? So we want to maximize 150 over 51 x1 plus 100 over 50 x2 plus 99 over 50 x3. Now, of course, the canonical linear programming problem, what are we supposed to be doing? Is this a canonical linear programming problem? We have non-negative real variables, we have our constraints involving non inequalities, and we're trying to maximize something. The way the canonical program is set up, this is not it. What are we supposed to do in a canonical problem?
There's a minimum for
It's a minimum. So how could we convert this to a minimum?
the dual.
We don't want to go to the dual.
Negative.
Yeah, negative, right? Instead of trying to maximize this, instead, multiply by -1 and minimize. No, but this should be funny, but this shows you the power, right? By having a canonical form, it doesn't matter if we want to do a maximum or minimum. It costs us a minus sign, right? No big deal. Okay, so now we all remember the simplex method, so let's roll up our sleeves and let's apply the simplex method to do this. So first, let's try to find a basic feasible solution here. Would anybody use the simplex method for this? How? And hell, we're not even going to multiply by a minus sign. We can solve this just by staring. Which variable can you immediately tell me how many we'll have? X3, right? X2 is the better per unit. What about, okay, now let's go one step further. X1 is better per unit, right? So the solution is X1 is equal to 100. So the profit is 150 over 51 times 100. And so I think I calculated what this was, $294.12 approximately. $294.12. Okay. So let's do a quick summary. In the integer case, the solution was 0, 2, 0, and we had $200. In the real case, the solution was 100. We've got to be a little bit careful now because I unfortunately have, I'm not saying this is $150 for a 51 kilogram unit, right? And so I should really be dividing this in some sense by 51 to say exactly how much of a 51 unit we have. This would be 100 over 51 unit 0, 0 for a profit of approximately $294.12. So the question is the optimal integer solution close to the optimal real solution? No. It's not just tweaking one of the coefficients a little bit. We are moving a sizable distance away. And this is one of the great difficulties in doing integer linear programming. We have powerful techniques to find optimal real value solutions. But we can't just say the optimal integer solution is close to the optimal real solution. So, as soon as you have one problem like this, you're in trouble. So there's two ways to go. One is to say, okay, well, maybe this only affects a certain type of problems, a certain class of problems, and there will be other problems where the optimal integer solution is close to the optimal real solution. And there will be some situations where it's like that. Imagine you're building a stock portfolio. Okay? Continuous or discrete? Discrete. But for all intents and purposes, you can almost regard it as continuous. If you're measuring prices of stocks in either cents or even in 1/8 of a cent, something like that, right? Then for all practical purposes, it's a continuous price. And when you're talking about buying 50,000, then the one little additional one makes such a small difference. So for a lot of problems like that, you could actually design your portfolio using real values. And then just take basically an integer solution that's close to that, and that should be pretty good. So there should still be a large class of problems that will be attackable with the methods we've done. Okay, so building a portfolio, that could be good. And then the classic example that I like to give is you own an airline or you're running a movie theater. You can't show 40% of a movie on the screen and not expect bad things to happen. Any European soccer fans here? I remember once in grad school I was a social chair, so I reserved the TV room for the World Cup. People wanted to watch that. The American networks didn't realize that the game could go over an hour or over 90 minutes if there are a shootout. And so the network then cut to a new program after 90 minutes. And all the people who had wanted to watch World Cup were furious. Right? You cannot watch 95% of a World Cup game and be happy if you're missing that final 5%. There's real consequences. We can't have 40% of a flight. Right? We can't show 40% of a movie. So unfortunately for issues like that, there's some extreme difficulties. And so the field of integer linear programming is a huge industry right now, trying to find efficient ways to do this. And so unfortunately, we cannot solve all integer linear programming problems in real time. What we can often do, however, is using the dual, we can often get close to the optimal in a given amount of time. So the example I did for the movie industry is we have 2 hours when we get the list of movies to when we have to determine which movie is on which screen and satisfy all the managerial constraints. And we allow ourselves to violate some of the managerial constraints if we think the profit is enough. And we will basically tell the manager, no, we're going to ignore what you want, because you're going to make so much money you'll be happy. We only have 2 hours, so we let the program run basically as long as we can let it, and then take the best value we get in that time frame. And we can often tell we're within 2% of the optimal solution. Okay, so the question becomes, what can you do with integer programming? What kinds of things can you do? So in integer programming, now the xi's on non-negative integers. There's a very important subclass of integer linear programming called binary integer linear programming. Now the xi's are in 0, 1. So think of it as on or off. So in the classic example, so xTMS is going to be 1 if at time t movie M starts on screen S and 0 otherwise. And now I can basically write everything about the movie theater in terms of these variables. What would be the corresponding variable if I wanted to do inlines? What variable would I need what subscripts?
In the error or not.
I'm sorry?
In the error or not.
See, you gotta be careful. I'm not saying whether or not the movie is on or off. I'm saying if the movie starts. I know how long the movie is, so I can then figure out how long I have to let it run.
Takes off.
Takes off. So I'll have some time t. Now what else do I need for my subscripts?
Flight time? No.
Flight time, I'll know.
Plane number.
So which plane is it? If at time t, plane P,
The lane?
I'm sorry?
Oh, I'm talking about the next thing. The screen I'm talking.
Right, it's what does the screen become?
Flight lanes, where they take off.
Good, where they take off from city A
To city B.
to city B. So it's 1 if at time t, plane P leaves A for B and 0 otherwise. And now we can do everything about airplanes. And this takes into account our plane. And then of course, we'll then add constraints such as once a plane takes off, it can't be used until it lands. Right? An interesting question is, and I don't know what the answer is, what happened after 9/11? I'm assuming you guys are old enough to at least remember 9/11.
The flight time becomes longer.
Well, no. Basically, very quickly after the plane started hitting the towers, what happened to all the planes?
They cannot land.
Well, the planes had to land.
But they cannot land as specific, like in DC or in New York area.
Not right, but it was more than just that. I think all planes were grounded. I think
I
they-
mean the planes in the air, because I just
Right.
heard a story that their plane was like shorting oil, but they cannot land in, so the pilot has to drive it back somewhere else. So it's
But I think after 9/11, I think the planes were supposed to land immediately. I'm not positive. But basically, all flights were canceled. And so now all of a sudden you have all these planes in different places where they weren't supposed to be, with people who didn't want to be where they were. Complete disruption of the network. It'd be, if somebody wants to, it'd be a very interesting project to look up and see how did the FAA and people actually get the air traffic system straightened out with all these people. I missed flying back on 9/11 by 2 days. I was coming back from my honeymoon in Hawaii. I had just been to Pearl Harbor and was thinking, it's nice that, days like this, like Pearl Harbor passed us. Almost had a much longer honeymoon. But you can now encode everything with something like this, and then you can start putting in constraints. And it would be very interesting, most of the time the system will be working, but then when a shock like 9/11 comes, it would be very interesting to see how they fix the system. You could do other things. You could do a Major League Baseball schedule. And this could be on the on day D, Team A is at home against Team B. And so if you want to do Major League Baseball, any schedule of any league. So, this is the day, and the first one is the home team, the second one is the visiting team. And so now you can come up with schedules as well. So everything fits into this framework. So what we'll do is we'll end with just trying to come up with one constraint. We've done movies before, we'll do airlines this time. And we'll just see how easy it is to formulate constraints. And then in the next lecture, what I'll do is I'm going to show you how a lot of things which may not seem like linear constraints can be converted to linear constraints. So again, one of the biggest restrictions of linear programming problems is all of your constraints have to be linear. And the objective function has to be linear. What if you have a nonlinear constraint? It turns out you can often linearize nonlinear constraints. But there's going to be a cost. So what do you think the cost will be to linearize a nonlinear constraint?
More variables.
More variables, right? There ain't no such thing as a free lunch, right? You want to linearize something that's nonlinear, you can do this at the cost of adding more variables. Is it worth paying that cost? Well, we have methods to solve linear programming problems, so frequently, yeah, it's worth paying the cost, because then we can put it in a framework that we can attack. Alright, so let's take the airlines. So somebody give me in words a natural constraint for an airline to have. What would be a reasonable constraint?
Budget constraint.
Okay, what would be the budget? What would be a budget constraint?
Like the amount of money they can use, or like the amount of resources they can use, or maybe time constraint.
So something like that is a higher level type of constraint where you're trying to determine how many planes you want to have. So for instance, I was talking with a colleague who is a high school teacher, and they're trying to design optimal bus routes. And so the question is, how many buses should you have? The more buses you have, the more expensive it is. But then the shorter time you have kids on the bus, and the more quickly and efficiently you can get kids to school. You don't want a kid sitting on a bus for 45 minutes. But of course, the more buses you have, the more expensive it is. So the number of buses or the number of planes itself could be a variable, and that could be limited by your resources. Now the problem is, I don't know if American Airlines can just all of a sudden say we want to rent out 15 Boeings for the next month, but then we don't want them, but we might want them again in 2 weeks. A lot of times you have to make big capital commitments, and you have to decide whether or not it's worthwhile. So that's where stuff like this is extremely valuable. So that's a good constraint to have. That's a much higher level constraint. Can you give me a lower level constraint? Something not quite as intense as how many planes to have. So who's been on an airplane? Come on. Who's been on an airplane? Okay. Okay, somebody need to volunteer. Somebody tell me where they've flown from and to. This is not a hard question. Give me a city you've flown from and a city you've flown to.
New York City.
New York City to where?
Shanghai.
Shanghai, okay. And was it a direct flight?
Both. direct and
Was it a non-stop flight from New York to Shanghai?
yeah.
Perfect. Alright, so you're going to fly New York City to Shanghai. So imagine you have a plane taking off. And so it's a very specific plane. So we have our collection of cities. So we have to have at least New York City and Shanghai and maybe some other cities in here. We have a collection of planes. 1, B2, Boeing names. We have times of day. Might as well say the times are 0, 1, 2, 3, 4. And so once a specific plane takes off from New York to Shanghai, what do you know about that plane?
Number of flight attendants.
No, more basic. If the plane is flying from New York to Shanghai, what is the plane not doing? Okay, so each plane can only be flying at a given time from one city to another, right? So, at every moment in time, each plane is flying between, at most, one pair of cities. Other constraints such as the number of stewardesses and everything, these are important, but in some sense screw the passenger if necessary. We can scrimp on that, right? Passengers will pay for luggage, they'll survive without the peanuts, we can deal with that. This, we cannot just check out the window, right? So at every moment in time, each plane can only be flying between one pair of cities. So this is our variable, YTPAB. At time t, plane P leaves city A for city B. And we know how long it takes. Let's let maybe R, A, B equal the flight time from A to B. So imagine at some moment in time, you have a plane going between two cities. Then you know it couldn't have started too far in the past, or it wouldn't be allowed, right? So let's see how we would try to encode this. And that's a good place to stop. So at every moment in time, so that's going to be for all t in that time set, each plane, so that's for all p in planes. So we're getting a lot of constraints right now. Right now, so far, you take the number of times and multiply by the number of planes. Each of those pairs is generating a constraint. Now, at most, you're flying between at most one pair of cities. So now if we sum over all A in cities, and we sum over all B in cities, then we look at, we start at time t. So now we're going to think about this. I'm going to use a capital T for time here. And so, at time t, plane P leaves city A to city B. And now I sum over all times from t minus the flight time. And I'll mention the mistake in just a moment, to my current time. The mistake is, this sum actually has to be right there. Right? Because the time window I look at depends on which pair of cities I have.
But also depends on which cities you choose, so it should be the other side.
So it should be the sum A in cities, the sum B in cities, and the sum t goes from t minus the flight time from A to B to our current time. So every time this is 1, it means a plane has taken off from A to B. Which plane? Our special plane, plane P. And it means then that plane P is in the air at time big T between A and B. We can have that plane in the air between at most 1 pair of cities. So what does this have to be? It has to be less equal to 1. And so look how easy it is to encode. Each plane is flying between at most 1 pair of cities at any moment in time. That's not a hard constraint to write down. That's a nice linear constraint. So whenever you're developing these mathematical theories, it's nice to see how robust they are. What kind of problems can they solve? This can actually solve a good number of problems. And any kind of constraint you want to add, you can put in here. Then the harder ones, as was mentioned, the more global ones. How many planes do you want to buy from Boeing? Do you want to buy it from Boeing? Do you want to buy it from Airbus? What kind of alliances do you want to make with other airlines? How many hubs do you want to have? Because, again, a lot of times we're not going to be having direct flights. And so all of these things can be put into a linear programming framework. It's going to be a very hard problem because these are integer values. Okay.